contrails have long been used for detection and tracking of aircraft. In November 1965, an optimized production model Contrail suppression system was demonstrated in flight on board a Model 147G special purpose aircraft. This film presents a summary of the efforts leading to the development of that system. The first attempt to employ a Contrail suppression system in a pilotless vehicle was conducted in 1962 using a BQM-34A drone with a J-69 engine. This program employed the Air Force Cambridge Research Laboratory's technique of contrail suppression. This technique was theorized in 1954 and demonstrated in flight in 1959 on a B-47 aircraft. In this technique, a mixture of chlorosulfonic acid and sulfur trioxide is injected into the tailpipe of the jet engine and mixed with exhaust gases, so that on condensation, many small droplets are formed. If the droplets are sufficiently small, the contrail will not be visible. 16 flight tests were conducted from November 1962 through January 1963. Because of improper agent injection, the system was ineffective in suppressing contrails. In August 1963, Air Force Cambridge Research Laboratories initiated a contrail suppression development test program at Holloman Air Force Base. The same basic contrail suppression concept was employed. An improved system was developed. Procedures were established for laboratory testing, which increased the reliability of the system. Significant improvements were made in injection techniques and nozzle design. For the first time, a complete instrumentation package was included to measure atmospheric and system operating parameters, providing valuable data on the formation and suppression of contrails. 56 flight tests in the BQM-34A were conducted from October 1963 through November 1964. Both ground and aerial photography coverage recorded system effectiveness. The following 3 film sequences show the system in operation. The contrail suppression system was proven effective at altitudes of 35,000 through 53,000 feet and atmospheric temperatures as low as minus 69 degrees centigrade. To meet an operational requirement, the results of the Cambridge Research Laboratory's Holloman Development Test Program were incorporated in a system for use on the Model 147B aircraft. In a single flight test at Eglin Air Force Base, Florida, the system was effective at altitudes of 50 to 57,000 feet in the moderately low temperatures that existed there. When deployed operationally at higher altitudes and more severe low temperature conditions, the system was ineffective. As a result, it was removed from operational use. From January through March 1965, the results of the Cambridge Research Laboratory's Holloman Development Test Program were thoroughly analyzed. This study revealed improvements which could be made in the system and technique. These were incorporated in the subsequent efforts. In May 1965, Air Force Logistics Command conducted flight tests of a contrail suppression system on a J-69 engine mounted in an RB-57F aircraft. 2 systems were assembled. Laboratory conditions were maintained in cleaning, assembly, and calibration of the test system. Each component and the assembled system were tested with agent under a chemical hood, both before and after each mission. In this manner, maximum cleanliness and system reliability was assured. The J-69 engine was mounted in the right outboard nacelle of the RB-57F. 2 agent manifold rings can be seen mounted in the tailpipe. This allowed testing of 2 injection nozzle configurations in each flight. The system was installed in the nacelle in the existing space available under the engine. Pressure gauges were left on until immediately prior to takeoff to assure system performance. Because the system had just been calibrated in the laboratory, a small amount of agent leakage occurred when it was connected to the tailpipe manifold. The availability of an RB-57F aircraft as a test platform made possible for the first time a controlled test program under operational environments. With a system operator on board, Test parameters could be varied in flight to achieve maximum test effectiveness. In this following film sequence, observe the right outboard contrail as it is being suppressed. Nine test missions were flown, 6 in the neighborhood of the Panama Canal Zone. This area was selected for its high altitude, severe low temperature environment, which closely duplicates that of the overseas operating area. In the flight test sequences, agent was initially injected at a high flow rate. Then the flow rate was decreased until the contrail reappeared. In this manner, the minimum agent flow rate required for suppression was determined. As this sequence continues, you may observe the contrail reappear. The purpose of this test program was to demonstrate the feasibility of the CRL contrail suppression system at altitudes above 58,000 feet, and to optimize the system by reducing the agent flow rate required for suppression. The system was proven effective in suppressing contrails at altitudes from 58,000 to 65,000 feet and temperatures as low as minus 75 degrees centigrade. Further, the system was optimized, reducing the agent flow rate required for suppression by approximately 40%. That is, from 75 pounds per hour to 45 pounds per hour. This program, as well as all previous contrail suppression efforts, was plagued by repeated hardware malfunctions. Valves, regulator, and heater assembly failures were common. At this point, a hardware optimization program was recommended. In July 1965, an optimized contrail suppression system was developed for use on the Model 147G special purpose aircraft, utilizing the parameters and techniques demonstrated and proven in the RB-57F flight test program. The objective was to provide a simple, lightweight, highly reliable, self-contained system. It would require no field servicing or maintenance. It would be easy to install and require no major modification to the vehicle. The system would employ the best state-of-the-art in component technology. Explosive-actuated control valves were selected, which had been developed and qualified man-rated for the Apollo and Gemini space vehicles. These valves have a statistical reliability of 99.996%. The pressure regulator selected has been proven and is being used in 34 other applications. The agent heater is epoxy bonded directly to the agent tank, eliminating troublesome heater blankets. The fluid system was enclosed and sealed in polyurethane foam. The insulated subassembly was then placed in a low-temperature chamber. The agent tank heaters were activated. The chamber temperature was reduced to minus 100 degrees Fahrenheit. The valves were then activated, and agent was dispensed. All of the system functional parameters were demonstrated in the laboratory under conditions closely simulating those experienced in flight. The molded foam subassembly, contoured to fit the wing fillet cavity, is installed with no modification to the vehicle. The wing fillet provides the necessary structural support. The nozzle assembly is fitted with a protective cover which is left in place on installation. This cover is burned away on engine start. The nozzle is installed through an access panel in the nacelle. 2 nozzles are installed in the tailpipe. They are supplied with agent independently by the left and right-hand assemblies. The optimized contrail suppression system was demonstrated over the White Sands Missile Range, New Mexico. 2 flight tests were conducted. a U-2 aircraft flew chase. When the system was activated, the contrail from the 147 was suppressed. From the ground photographic film, you can see the RB-57F photoplane and its contrails on the left. On the right is the contrail produced by the U-2 chase aircraft. The U-2 is barely visible. In the center screen, leaving no contrail, is the white 147G aircraft. The system performed as intended and satisfied all its design objectives. By a series of efforts, a contrail suppression system has been developed for the Model 147G special purpose aircraft. The contrail suppression technique was first demonstrated on the BQM-34A. Then, utilizing a manned test aircraft, the technique was optimized for operation about 58,000 feet at conditions simulating the actual operating environment. Then a simple, highly reliable, self-contained and maintenance-free system was developed, capable of 2 hours continuous suppression. The use of this contrail suppression system on the Model 147G aircraft can greatly increase its survivability.